My day job is in a systems engineering company called Guardtime, and I will have a talk about my work at Guardtime, or a talk about the topic related to my work at Guardtime on Saturday afternoon. Today here I'm talking about a topic that I became in contact with because I'm one of the organizers of the Estonian Olympiad in informatics. And the Olympiad in informatics is basically a programming competition. I had a short talk about trying to give an overview of what programming competitions are all about. Last year, it is in this conference. I think the video should still be up on YouTube. If you think this is something you want to have more background on, this could be a place to start. But in short, despite the name Olympiad in informatics being slightly vague, maybe, it is essentially a programming competition. And the naming issue goes back to 1987, when the first informatics Olympiad in Estonia was held. And the word Olympiad has been used for science competitions for high school students for a lot longer than that. There have been Olympiads in mathematics, physics, chemistry, things which basically are problem-solving contests. So the jury prepares some slightly tricky, non-trivial problems, and then students competitively solve them. It's kind of like a special version or extended version of a quiz, where the answers are not something that you know, but something that you have to figure out. And programming competitions joined this family of science Olympiads in late 80s in Estonia, when informatics was introduced to schools. And at this time, informatics in schools was actually about algorithmics and basics of programming. And this was done in most schools with pen and paper or a chalkboard, because there were not so many computers to go around. At least the PC revolution hadn't still gotten to Estonia at this time. But there were also some schools had computer labs, and some other schools then occasionally made trips to those schools so that kids could actually try out their programs on actual computers. And the class was called informatics, which was heralded as a next literacy. And this is how the name informatics got stuck to the programming competition, which it is still called like that. And so the same name is also used for international competitions, which basically are programming competitions. And the competition is about designing and implementing correct and efficient algorithms to solve given data processing problems. And then the correctness and efficiency of the programs is evaluated by typically in contest setting, is typically evaluated by black box testing. So there is a bunch of test cases for different situations that the program is supposed to handle, and those test cases are fed into the program that the student has written and has uploaded to a grading server, and then the student gets feedback and gets some score based on how many of the test cases his or her solution solved correctly. So this is the correctness part, but also the efficiency part. We can't, of course, automate analytic analysis of algorithmic complexity. So the efficiency of a program is graded by setting time limits and memory limits on each test case. Typically, the limit is set once per task, and then the efficiency of the program is graded by feeding it into increasingly larger and larger or more difficult test cases, and then then basically seeing how far it gets before it starts to exceed the allocated time and memory limits, and then who gets further gets better score. And really, because the intent of the competition is designing algorithms, then at least in the lower leagues of the competition, we don't want to push the students too hard on practical implementation, optimization details. One of the reasons is some of the things are really basic and don't take any time during competition, but one of the reasons is that the competitive programming happens under heavy time constraints. Typically, in a competition round, there are something like 3 to 5 problems to be solved in 3 to 5 hours. So this basically gives a student 1 hour to read the problem statement, to understand, to extract the mathematical model, to understand what is needed, to think of an algorithm to do this, and then to implement and submit it. And that is quite a lot to do in 1 hour. And so basically the intention of the organizers or the jury is to focus on the algorithmic complexity of the solutions. So suppose there is some kind of data processing problem that gets as input a sequence of n integers and then does something with those integers and outputs either a resulting sequence also of n integers or perhaps just 1 integer, something that is computed from this set. And the jury wants to distinguish between algorithms running in linear or quadratic time. And then, of course, if you think about one thing is a mathematical ideal algorithm that kind of takes a mathematical object of sequence of integers and does something with it. Other one is an actual program, and the actual running time of a program is if the algorithm has linear complexity, then actually the actual running time is A, which is the program startup cost. Then B plus N, which is the time to read the input and write the output, which has really no relevance for the content of the task. And then C times N for the amount of work that is done actually solving the problem once the data has been loaded into memory and to get the answer and then to write out the answer for grading. And then for ON squared algorithm, the constant and linear parts are still there, of course, because the less efficient algorithm also the program has to start up and has to read the input and produce the output. So this is roughly we can expect to be the same. And then there is this n squared part, which is time part, which is actually solving the task. And one of the things is that typically, because the B, the linear part operations involve input and output, so the multiplier on those operations is much higher. Reading an integer from a file or writing an integer onto the standard output takes a lot more time on a computer than handling this integer while it is in memory. So the question that we as a jury have to solve for every task is how large an n do we need so that the linear parts, the kind of fixed costs, do not overwhelm or overshadow the linear versus quadratic part, the actual algorithmic parts that we want to measure and that we want to grade. And so in practice, actually, it is even worse because the real running time of the program is the B1 and B2 for the algorithms. They might also be, so for the algorithm, of course, it doesn't depend on the algorithm, but depending on how the student implements the reading of the input or the writing of the output, then actually the multiplier on this linear component for doing the input-output part, the multipliers might differ between different implementations. And again, this is a non-essential technical detail which does not depend or does not reflect on the student's algorithm, which we want to grade. And in some higher level competitions, we can expect that the students are experienced competitive programmers, and we can expect that they know how to do input-output efficiently in their chosen programming language. But in the first rounds, where the beginners come in who haven't done competitive programming before, we don't want to impose such limits. In fact, in the very first rounds for the younger students, the tasks are such that and time limits and the input data sizes are such that basically any correct algorithm gets accepted as long as it produces the correct answer, and then only in the middle levels we start pressing for efficiency. But then also we want to start from the principal parts and ignore the non-essential technical bits for as long as possible. And so for that reason, in theory, we need to know what the different values of B are, B1, B2, depending on which way the student does the input, because we want to ensure that an efficient, principally efficient algorithm, which uses an inefficient way to do input-output, passes the tests. And on the other hand, we also want to ensure that an inefficient algorithm cannot buy too much by doing I/O efficiently. So if you do a quadratic algorithm, but you do blindingly fast input and output, this should not give you the score that was intended to be given for the linear complexity algorithm. And so for this reason, I did a bunch of tests for measuring what different ways of doing input-output in obvious and non-convoluted ways in C++ are, and what are their costs in terms of running time. And so I have a simple script which in the code examples below here. Do I have a clicker? No. Apparently the pointer doesn't work on the screen very well. So the point source in the code samples on the bottom of the slide, this is just a simple program to take two parameters from command line and generate n lines with m integer values on each line to simulate different workloads on the thing under test. And then this .pipe part is execution of the student's solution. And I made two kinds of tests, reading the input from a text file and writing the output to another text file, or then using pipes so that the actual physical disk does not come into play. Because these are the two ways how a graded program can be executed inside the evaluation environment. And for those two scenarios, I wanted then to see what is time to read the input into memory and then copy to output using standard input-output functions from C, using the C stdio library, calling it from C++ program. This is just to see if there is a difference between C and C++, which I expected there not to be. And then the actual part of the interesting part of the test was using C++ iostreams library. And specifically, I wanted to know what the effect is of doing or not doing the iOS sync with stdio, and doing or not doing the tying between standard input and standard output streams. And then one common thing that beginners also tend to do is when they just want to output a new line, they tend to use the endl IO manipulator, which does the new line and also does flush output buffer. And this I expected to be a major impact on the program's running time. And the test results that I show on the next slide, they were obtained by GCC 9.2 running on Ubuntu 20, and all the code examples were compiled with O2 level, optimization level, because this is what we have in the grading environment right now. And of course, since I already now have the scripts, I could run the test on other compilers and other operating systems and so on. But it's probably the other compilers and other libraries might have an effect. Doing it on other operating system probably shouldn't change the results too much. And then the results, I did tests with 1 million and 2 million lines, because anything less gave very small running times, and this simple 100-second precision that the time command of bash gives didn't really have too much accuracy otherwise. And I experimented with 10 and 20 numbers per line. So altogether, we're talking here about processing 10 million to 40 million numbers in those those tests. And this is kind of the size where the standard, when you run the experiment a few times, and the variance from one experiment to another is small enough that you actually can draw some conclusions. And as expected, there was no difference between runtime in the runtime of the programs between using C stdio from C and C++ code. So the same library code works at the same speed, whether it is called by C or C++ compiler. So no surprise here. When using C++ iostreams and using like normal end-of-line character, then by default, this was about 11 times slower on actual files, disk files. So when the input was read from a file and output written to another file, and about 8 times slower than the baseline, which was using the C-style stdio library when using pipes. So I didn't actually expect there to be this difference, which is about, come to think, it's more than 30% difference. And I don't know how to explain this. I would expect that the hit that you get from going to disk is or the hit that you get in CPU time usage is the same whether you go to disk or whether you go to pipe, but for some reason there was a difference. And the C++ iostreams were about 9 times slower on files and 7 times slower on pipes when using just the unsync. So it seems synchronization with between the C++ iostreams and the C-style standard input-output it does not cost too much. Turning this off changed the results by less than 20%. And the C++ iostreams were about 1.5 to 2 times slower than the stdio when using just untie. So just when the standard input and standard output the stream objects in C++ were untied from each other. And maybe one thing that is worth mentioning is that I really did the processing of input-output very gradually. So every integer I read from the input, I copied it to the output at once. Perhaps the ratios would be different if I would read a line at a time, and this is maybe an interesting follow-up experiment to do. But for now, we can, I think, as far as judging of the solutions is this ballpark number of 1.5 to 2 times. This is good enough result. So, and a bit to my surprise, when untie and unsync both were applied, then the C++ version of the program actually ran 10 to 20% faster than the one using the C-style standard input-output. So this is a result that I didn't expect, but then 10 to 20%, this is not a small, not a large difference compared to the 10 times and 2 times runtime differences that we saw in other cases. And there was also another surprise for me personally was that there was no big difference between using a normal end-of-line character and using the endl IO manipulator as a line terminator. I expected there to be a big difference. And only case when both untie and unsync were applied, so we were already in the realm where the runtime of the program was the same as with the C standard input-output library, then using endl instead of a proper new line made a difference. And also there was no big difference between doing million lines of 20 numbers versus 2 million lines of 10 numbers. So the total number of numbers processed was the same, but the number of times new line was output was different, and this didn't really make a difference. I didn't expect it to make any difference with just a new line character, because writing a space versus writing a new line character should not make a difference. But I was expecting that this using endl instead of regular line end makes a difference all the time, but it only made a difference again in this maximum optimized case where untie was used.